Hello and welcome once again to the Aakash BYJU'S YouTube channel. My name is Atiullah and we are live once again with JEE Mission 2022. Alright guys, a very warm welcome. We are doing Nuclei and Radioactivity, and in this session we are going to take up previous year and some important questions. So before we begin this session, please let me know if you can see me properly and you can hear me clearly. Just give me a yes, give me a thumbs up so that quickly we can get started with this session. Alright, quickly guys, just let me know if you can see me and hear me. There's no problem, there's no technical difficulty, there's no issues anywhere. If all is clear, then we are going to get started with the session. Alright, are we good people? I think people are still joining in, so we are going to wait for a few seconds. Alright, perfect. Let's start. Okay, so in this session we are taking up nuclei and radioactivity, which I have emphasized a lot. It's part of modern physics and it is very simple chapter, very scoring chapter, so we should not miss that. And we are going to solve previous year papers, so obviously you will get an idea of what is the difficulty level of the problems. Okay, so that is also going to give you a lot of confidence. If you have studied the basic concepts well, then I assure you, you are not going to face any difficulty. Alright, so people joining in, Anshuman, Alok, Mayfly, very good evening people. Welcome to the session. And you know the drill, let's get cracking with this session. I'm going to throw questions at you. You're going to solve them together with me and we are going to discuss all the concepts, revise all the concepts. Alright, so here we go with the first question of the session. Are you guys ready? Here we go. So we have two deuterons. Yeah, so we have two deuterons undergo nuclear fusion. Okay, so they undergo nuclear fusion to form a helium nucleus. Okay, two deuterons. What are deuterons? Can anyone tell me? So deuteron is 2H1. Okay, it's called heavy hydrogen also. So it has one proton and one neutron. So the mass number is 2 and the atomic number is 1. Okay, so they fuse together to form one helium nucleus. The energy released in this process is, now what is the data given to us? That the binding energy per nucleon for deuteron is 1.1 mega electron volt and for helium it is 7 mega electron volt. So what is this binding energy per nucleon? Alright guys, so take a few seconds to read the question, to attempt it, and let me know what is the basic concept involved to solve this question. Okay, once we have discussed the concept, then we are going to go ahead and solve the problem. Okay, so quickly I want to first get your understanding. What is the concept involved? Do you recall the concept? Are you able to remember the concept? Quickly let me know. So here we are talking about a few things. We are talking about fusion. We are talking about binding energy per nucleon and how that is going to affect this equation, right? How that is going to affect, that is going to have an effect on the energy which is released or absorbed in the reaction, in the nuclear reaction. Alright, so we have Ram Prakash also. Very good evening Ram Prakash. How are you doing? Alright people, quickly tell me what is the key concept involved in this question. Alright, so let's see. Now what we have here is that we have two deuterons which fuse together to form one helium nucleus. Is that right? So this is the equation that we are looking at. This is the nuclear reaction we are looking at. Okay. Now if we talk about the binding energy of the reactants, okay, we are talking about the binding energy of the reactants. And binding energy per nucleon So we generally denote it by Bn, binding energy per nucleon. That is given by binding energy divided by the mass number. Okay, what is mass number? Mass number is the total number of nucleons. So binding energy per nucleon is the binding energy divided by the mass number. So if I have to calculate the binding energy, then that's very simple. Binding energy would be the mass number multiplied by the binding energy per nucleon. Is that correct? So when I'm talking about the binding energy of the new reactants, what can I see? So this is 2H1. The binding energy per nucleon is 1.1 mega electron volt. And how many nucleons are there? There are 2 nucleons. Okay, so what will be the binding energy? The binding energy would be 2 multiplied by 1.1 mega electron volt. Okay, so this is for one deuteron, and for the second deuteron, the value is going to be the same. So what I can do is I can simply multiply it by 2. So the binding energy of the reactants comes out to be 4.4 mega electron volt. Do you agree? That is the binding energy of the reactants. Now let's talk about the binding energy of the product. Okay, there is only one product, and that is 4He2. Now the binding energy per nucleon is 7 mega electron volt. And how many nucleons are there for helium? The mass number is 4, which means that the number of nucleons would also be 4. Is that right? Okay, so the binding energy product is going to become 4 multiplied by 7, which is 28 mega electron volt. Is that clear? Is that correct? So what is happening over here? The binding energy of the product is going to become larger. Okay, the binding energy of the reactant is 4.4 mega electron volt, but the binding energy of the product is 28 mega electron volt, which means that the energy which is released in this reaction is going to be the binding energy of the product minus the binding energy of the reactant. Do you agree? And if we do this calculation, very simple calculation, we are going to get 23.6 mega electron volt. Okay, and that will be the energy released in this nuclear reaction. Is that correct? Okay, so what we see here is that if the binding energy of the product is greater than the binding energy of the reactant, it means that the product that is formed is much more stable, and hence the energy is going to be released. Okay, and if the other way around were true, for example, the binding energy of the reactant was greater than the binding energy of the product, then that would mean that the product is less stable than the reactants, and energy has to be supplied to make the reaction happen. Is that correct? Is the concept clear? Alright, yes Alok, you are absolutely right. 23.6 mega electron volt, not electron volt. Mega electron volt is going to be the right answer. And if this is clear, let's look at our options. So 23.6 mega electron volt, option C is going to be our right option. Okay. Now look at this question. This question came in JEE Main. Trust me, this is a question that came in JEE Main. And how difficult was the question? So my objective here is also to give you the confidence that JEE Main is not difficult. Okay, and especially the modern physics part is not difficult at all. Is that right? Alright, so with that said, let's move to the next question. Okay, another question on nuclear fusion. So in the nuclear fusion reaction, so we have 2H1 and then we have 3H1, and they react to form 4He2, and there is a neutron as well. Alright, so this is the reaction, this is the fusion reaction. Now it is given that the repulsive potential energy between two nuclei is 7.7 into 10 to the power minus 14 joule. The temperature at which the gases must be heated to initiate the reaction is nearly, and we have been given the value of Boltzmann's constant. Okay, now think about this question for a second and let me know the concept. Okay, the concept here is very important. So please tell me that what is the concept involved. Let me know that you know the concept, and if you don't know the concept, no worries, I'm going to revise that for you. But first I want to understand from you, what is the concept? What is the criterion for a fusion reaction to take place? What is the most important thing for a fusion reaction to take place? Alright, more people joining in. Sachin, very good evening. Aakash, Sheikh, Hyper Gaming, very good evening and hello. So I hope you guys are following the sessions, you guys are revising, and once the session is done, you're going back and revising yourself also. That is very important. Okay, go back, do the same questions without looking at the solutions, or even just pick up any random thing, okay, any random test paper, any previous year paper or any test material, and start solving that. All right, Nitesh is saying, sir, dates are out for JEE. Yes, dates are out for JEE, and are you excited? That's a very exciting time for me, because a lot of my students reach out to me and ask me what should be done, what should not be done. Okay, I help them calm down also. But I want to know from you, Nitesh, are you excited or are you afraid? Tell me. What's the feeling? The JEE dates are out now that you know that you have been preparing for that exam for some time now. And so how does it feel that when you know finally that, okay, this is the date when we are going to take this exam? Do let me know. Alright, Keshav Raj is saying KT is equal to given energy. Okay, now let's talk about this. Now if we have these two nuclei, and fusion has to take place, then they have to come in a very close contact. Okay, what kind of close contact? They have to come such that the distance between them is nearly equal to the nuclear range. Okay, and obviously there's going to be repulsion because nucleus is positively charged, so there's going to be repulsion. So the kinetic energy of the particles should be so much, okay, the kinetic energy of the particles should be so much that they are able to overcome the electrostatic repulsion. Is that right? Okay, so what is the kinetic energy of these particles? Okay, so these are gaseous molecules or gaseous atoms. Okay, these are in gaseous state, and so these would be in the form of gaseous atoms. And what is the kinetic energy of a gaseous atom? Right, so we know that the kinetic energy is given by 3/2 kT. Okay, for a single atom, the kinetic energy is given as 3/2 kT. Now this kinetic energy should overcome the repulsive potential energy, which is 7.7 into 10 to the power minus 14 joule. Is that correct? Okay, so from here what do we get? We get T is greater than 7.7 into 2 divided by 3, then we have 10 to the power minus 14, and in the denominator what do we have? In the denominator we have the Boltzmann's constant, which is 1.38 into 10 to the power minus 23. Okay, so we don't need to do this calculation because we just need to know what is the order of the temperature. Okay, so this is going to become approximately 10 to the power 9. Yes, this is going to become 10 to the power 9. So the order of the temperature is 10 to the power 9 Kelvin. So that is going to be my answer. So let's check the options. So option D is going to be the correct option. Is that correct? Alright, so Alok is saying temperature should be such high so that it has enough kinetic energy to overcome Coulombic repulsion for nuclear fusion. Bang on Alok, absolutely right answer, and that's exactly the concept we have used to solve this. Okay, Hyper Gaming is saying, sir, excited but little bit nervousness. Okay, so I understand that. Okay, I understand that there will be a little bit of nervousness, but trust me, a little bit of nervousness is very good. Okay, that makes us work, that makes us attentive, that makes our blood flowing, that makes our adrenaline flowing. Okay, so that is helpful. So that is that's the pump, that's the kick you need to focus and to work in a very attentive manner. Okay, so that's good. But guys, there's nothing to be afraid of. We have been solving previous year papers. So if you have been following us, we have been solving so many previous year papers, and what are several sessions we are doing? Our objective is to make you understand that if your concepts, even your basic concepts are fine, then you are not going to face any difficulty in JEE Main. It's not a difficult exam. Okay, it's all about getting the basics right. That's all. And a lot of people that I have been interacting with here, I think they are doing very well. They're doing very well with their basics. They're very attentive. They're very engaging, and I think their preparation is going on the right strategy. So yes, so we are getting a little deviated, but my best wishes to all of you. Okay, don't be afraid of JEE Main. Trust me, it's not a difficult examination. Just focus on your strengths, focus on revising well, focus on not making mistakes, focus on not getting overwhelmed, focus on not getting anxious, okay, sleep well before the day of the exam and take it easy, man. It's part of life. It's not your entire life, okay? It's a part of life, a very important part of life, because you have been putting a lot of effort, but it is a part of your life, okay? So whether you succeed, you don't succeed, don't focus on those things. Those are very negative things to focus on. All you need to focus on is that you are giving your best, okay? You are able to perform your best, okay? So there are things which, like, you got nervous, you got anxious, or there was something happening in your life that which kept you distracted, okay? There's some stress, there's some tension. Now all these things are something that you don't need, okay? You don't need these things. This is going to bring your performance down. So whatever your preparation is, however good your preparation can be in these few months, do that and make sure that nothing deters that, okay? You are able to perform your best. That's all you need to focus on, nothing else, okay? क्या होगा नहीं होगा ये सब के बारे में सोचना ही नहीं है. All you have to do is whatever you have prepared, whatever best you can do, you're going to do that, okay? That's all you need to keep in mind. All right, okay, so Darshit is saying, sir, there will be negative marking in numerical too. यार it's okay, don't worry about negative marking, ठीक है? नेगेटिव मार्किंग अगर तुम्हारे लिए है तो नेगेटिव मार्किंग सबके लिए है, ठीक है? अगर तुम मिस्टेक करोगे तो बहुत सारे लोग मिस्टेक करने वाले हैं. Is that right? Okay, so the pattern is the same for everyone. तो डिफिकल्ट भी है तो सबके लिए सेम डिफिकल्टी है, इजी भी है तो सबके लिए सेम इजी है ना? तो कंपटीशन है, तो इसमें अपने को ये नहीं सोचना है कि ये पैटर्न क्या है, वो पैटर्न क्या है. पैटर्न से कुछ फर्क नहीं पड़ता है. इन JEE एडवांस एवरी ईयर देयर इज अ न्यू पैटर्न, right? So we don't need to worry about pattern. What we need to worry about is the concepts. If our concept is right, so whatever be the pattern, we will be able to solve it. So don't worry about those things. Don't worry so much. Just just focus on your preparation. Just focus on being, and that's the word here. Focus. Okay. You just need one thing. You just need to aim at one thing. Nothing else. Okay. Don't look at anything else. Don't worry about anything else. Just focus on one thing, and I'm sure you're going to do well. All right. So, बहुत सारा फंडा हो गया. Now let's get back to our session. Okay, because जितना भी फंडा हम लोग ले लें, जितना भी फंडा दे दें, ultimately what is the thing which is going to get you through? Okay, it's what you have studied, right? That's all. Okay, so let's get back and let's focus again on studying, right? So let's go for this question. So we have lithium-37 nuclei are bombarded by protons and the resultant nuclei are beryllium-4-8. Okay, 8 is the mass number, 4 is the atomic number. The emitted particles will be, okay, what are the options? The options are alpha particles, beta particles, gamma photons or neutrons. Okay, so quickly tell me what is the concept involved over here. Okay, very simple question, but I want to understand from you what is the concept involved. How are you going to solve this problem? Alright, so what do we have? We have 7 lithium-3. Now this is bombarded by a proton. Now what will be the mass number and the atomic number for proton? Okay, so obviously one proton means one atomic number. So proton itself will have an atomic number of 1, and the nucleon, one nucleon, so it will be 1p1. Okay, so the right way of writing the mass number and atomic number for proton would be 1p1, correct? Now this combines and forms 8 beryllium-4. Now what happens in a nuclear reaction? In a nuclear reaction, the mass number and the atomic number, the charge has to be balanced. Is that right? Okay, it's a nuclear reaction. It's an equation, which means the mass number, the total number of nucleons, the total number of protons, and the charge has to be balanced on both sides. Is that correct? So can we check? So we have number of nucleons 7, number of nucleons 1. So 8 on the LHS and 8 on the RHS. So number of nucleons is balanced. What about the atomic number? 3 over here, 1 over here, 4, and 4 on RHS as well. Okay, so this is also sorted. What about the charge? The charge is also going to be sorted. Okay, so if we have an alpha particle, this alpha particle is going to disbalance the equation, because alpha particle, what is alpha particle? 4He2. Okay, now mass number and atomic number is already balanced, so we cannot have a particle which has any mass or charge. Do you agree? Which cannot have any mass number or atomic number. It is going to, if we add that in the RHS, then it is going to disbalance the equation, correct? So what is the option that is left? Obviously the only thing that can happen is there can be a gamma photon, because gamma photon is only energy, it does not carry any charge, or it won't have any mass number or atomic number. Okay, so what will be the correct answer? The correct answer for this question is going to be gamma photon. Okay, such a simple question, probably it will take 15 to 20 seconds for you to solve this, right? Alright, now let's go to the next problem. Okay, now we are back with law of radioactive decay. Now half-lives of two radioactive nuclei A and B are 10 minutes and 20 minutes respectively. If initially a sample has equal number of nuclei, then after 60 minutes the ratio of decayed nuclei of A and B will be. Okay, that's the question. Okay, so read the question and try to solve this, but before that just let me know what is the key concept involved. Here's the question for you. Alright, so obviously the concept involved here is the law of radioactive decay. Now law of radioactive decay tells me that the number of active nuclei at this time t will be equal to n naught into e to the power minus lambda t. Okay, n naught is the initial number of nuclei, lambda is the decay constant, and t is the time. Now there is another way of writing this equation. If you take log on both sides, okay, there is another way of writing this equation. Probably we discussed this in the session yesterday also. So we can write this as n is equal to n naught divided by 2 to the power t divided by t half. Okay, t is the time and t half is the half-life. Okay, so how many half-lives are there? That will be given by t upon t to the t upon t half, and the number of nuclei remaining is going to be n naught divided by 2 to the power t upon t half. Simply n naught divided by 2 to the power number of half-lives. Is that correct? Okay, so this is also a very good way of representing this equation, and sometimes it makes our problem solving much simpler. Is that correct? Okay, now let's talk about nuclei A and B. Initially the sample have equal number of nuclei. So let's say initially A also had n naught nuclei and B also had n naught nuclei. Now after time, how much time is there? After 10 minutes. Okay, after time, or they have, sorry, I'm sorry, the half-lives are 10 minutes, my bad. The half-lives are 10 minutes and 20 minutes, but after 60 minutes, let's see how many nuclei are remaining. Okay, so can we write n is equal to n naught divided by 2 to the power, and what do we have over here? We are going to have the time, which is 60 minutes, divided by the half-life, which is 10. Okay, so we are going to get this as n naught divided by 2 to the power 6. Is that correct? So that is the number of nuclei of A which is remaining. Now what about the number of nuclei of B? So we can write it as n naught divided by 2 to the power, the time is 60, and then divided by 20, the half-life for nuclei B. So this is going to be n naught divided by 2 to the power 3. Is that right? Okay, so this is the number of remaining nuclei of A, this is the number of remaining nuclei of B. But what we are interested in is the number of decayed nuclei. What will be the number of decayed nuclei? Very simple, number of decayed nuclei would be the initial number of nuclei minus the number of nuclei which are remaining. So this is the number of decayed nuclei. And similarly for B, we can find out the number of decayed nuclei as n naught divided by minus n naught divided by 2 to the power 3. And what we have to find out is the ratio of these two quantities. That's all. We have to find out the ratio of these two quantities. So if we take the ratio of these two quantities, what are we going to get? N naught is going to get cancelled. That's very simple to see. Then we have 1 minus 1 upon 2 to the power 6, and we'll have 1 minus 1 upon 2 to the power 3. So in the numerator we'll have 64 minus 1, 63 divided by 64, and here we are going to have 8 minus, so this is 8 minus 1, 7, and 2, 3, 8. This is going to go upstairs. So this is going to become 9, this is going to become 8. So my answer is going to be 9:8. Is that correct? Okay, so the correct answer is going to be 9:8. Is that clear? Okay, so the important concept that I wanted to revise for you is that sometimes if you use n naught, n is equal to n naught divided by 2 to the power t upon t half, it can make your calculation a little bit simpler. Is that right? Okay. That's it. Yes, Alok, you're absolutely right. 9:8 is the correct answer. Mayfly, you can probably check your answer. Probably some calculation mistake. Hypergaming. Yes, absolutely right. That answer is perfect. Alright, so simple question. Again, I'm emphasizing this is a JEE Main question. What was difficult about it? Right? Nothing. Let's go to the options. So option A is going to be the correct option. And now let's move to the next problem. Using a nuclear counter, the count of rate of emitted particles from a radioactive source is measured. Sorry. At t is equal to 0, it was 1600 counts per second. Okay, at t is equal to 0, the activity was 1600 counts per second. At t is equal to 8 seconds, it was 100 counts per second. The count rate observed as counts per second at t is equal to 6 seconds is close to. Alright, so that's the question. That's the question. Quickly try to solve that. Okay, so number one thing you should think is, what is the concept involved? What is the key concept that we need to revise over here? Okay, and it's the same. There is radioactive decay. So as I said, for radioactive decay, sometimes we can write n is equal to n naught divided by t to the power t half. Right, so let's try to apply that. Okay, so let's try to apply that for t is equal to 8. Let's see what happens. So what is the count now? The count now is 100. What was the initial count? The initial count was 1600. Okay, so initial count divided by 2 to the power, what is the time? The time is 8 and then t half. Is that correct? Have I written this correctly? Can you tell me? Can you confirm? This is n is equal to n naught divided by 2 to the power t divided by t half. Correct? Okay, so from here what do we get? We get 2 to the power 8 upon t half is equal to 16, and 16 I can write it as 2 to the power 4, which means 8 divided by t half is equal to 4, which means this data was given to me to find out what is t half. Okay, so t half comes out to be 2 seconds. Is that clear? So we have figured out that t half comes out to be 2 seconds. Clear? Perfect. Now if this is clear, now let's think how many half-lives have gone. Okay, so how many half-lives have gone? So 6 seconds divided by 2 seconds, which are 3 half-lives. Is that correct? So what happens in 3 half-lives? The activity was 1600. In 1 half-life, it is going to become half. So this is going to become 800. In the next half-life, it is going to become 400. And in the next half-life, it is going to become 200. Okay, so at the end of 2 seconds, what will be the activity? The activity is going to be 200 counts per second. Is that clear? Yes, Alok, perfect. Alright, so I am solving it using a certain method. Now if there is anything which you know or you have tried which can help us solve this question in a quicker manner, please share that with us. Okay, that will be a good addition, or there will be a good knowledge for everyone. Okay, if you know there is a faster method, if you know there is something which can help you solve the question in a much simpler manner, do share with us. Okay, I'd love to see that from you guys. Alright, so option C is going to be the correct option, And now let's move to the next problem. Alright, what do we have? A radioactive nuclei with decay constant of 0.5 per second is being produced at a constant rate of 100 nuclei per second. Sorry guys, just a moment, but you guys can read the question. Alright, so go read the question and start solving. I'll catch up. Alright, so if at t is equal to 0, there were no nuclei, the time when there are 50 nuclei is. That's the question. Think about it. So the difference here is, difference between a normal scenario and this scenario is that a radioactive nuclei is being produced. Okay, it is being produced at a certain rate. And if it is being produced, it is also radioactive, so it is also going to disintegrate. So we need to find out what is the rate of formation of this radioactive nuclei. Alright, so let's think about that. Okay, so what do we have? Let's say R is equal to 0.5 per second. What is R? Sorry, lambda is equal to 0.5 per second. I'm sorry, that's the decay constant. Lambda is 0.5 per second. And then it is getting produced at a rate of 100 nuclei per second. So I'm going to write R, the rate of production, as 100 nuclei per second. And we are saying that when n is 50 nuclei, when there are 50 nuclei, what will be the time? That's the question. Alright, so let's think about this. Okay, now I am talking about the rate of formation of this nuclei, the rate of formation of this nuclei. Now there is the rate of production. Okay, what is the rate of production? Rate of production is R. Okay, and if there are n nuclei, then what is the rate of disintegration? The rate of disintegration is going to be lambda n. Is that correct? This is the law of radioactive decay. The rate of disintegration is proportional to n, which means the rate of disintegration is lambda n. So it is getting produced at a rate of R and it is getting disintegrated at a rate of lambda n, which means the net rate of production is R minus lambda n. Do you agree? The net rate of production is going to be R minus lambda n. Is that correct? Okay. So now we can interchange this. So this is going to become dn upon R minus lambda n, and this is going to become dt. Alright, so we have got this in the form so that we can integrate. Okay, so this is going to go from 0 to t and this is going to go from 0 to n. Initially there were no nuclei of A. Now let's quickly integrate this. So this is going to become ln R minus lambda n, and then we'll divide it by the coefficient of n minus lambda, and then we'll put the limits from 0 to n. Okay, on the RHS we'll get t. So this is the t we need. Is that correct? Okay, this is the t we need. That's all. So we need to just solve for the LHS. Okay, now if we solve for the LHS, what are we going to get? We're going to get ln R divided by R minus lambda n divided by 1 upon lambda. This will be equal to t. Now check and let me know if this makes sense. Alright, check if the calculation is correct, if the limits have been properly inserted. Just check that and let me know if this is fine. Okay, so the time will be given as 1 upon lambda ln R upon R minus lambda n. Okay, so I'm going to write it over here. T is equal to 1 upon lambda ln R upon R minus lambda n. Okay, now all we have to do is do the substitution. So what is lambda? Lambda is 0.5. Then we have ln. What is R? R is 100. And we have 100 minus lambda is 0.5 and n is 50. That's it. So what are we going to get? We are going to get 2 ln 100 divided by what? 100 divided by 100 minus 25, which is 75. So this is going to become 4 by 3. So we are left with 2 ln 4 by 3, and that should be our answer. Is that correct? Clear? So what is the difference between this problem and a problem in which there is no rate of production? Okay, there is only disintegration. Here we'll have to take the net rate of formation of A, that is the rate of production minus the rate of disintegration. Is that clear? Alright, perfect. So what will be the correct option? The correct option is going to be obviously option B. Is that clear? All good? Perfect? Awesome. So now let's go to the next question. So we have a radioactive nucleus A with half-life capital T and decays into nucleus B. At T is equal to 0, there is no nucleus of B. At some time T, the ratio of the number of B to that of A is 0.3. Then T is given by. Alright, read the question carefully. Make sure you understand the question and then go for it, solve it and quickly let me know your answer. Or if you want to discuss the concept, I think there's not much to discuss about the concept. It's just law of radioactive decay. So quickly solve it and let me know what is the answer and what is the process that you followed. Alright, so A decays to B. So let's say at T is equal to 0, there were N0 nuclei of A, which means there were 0 nuclei of B. So it is given in the question that initially there are no nuclei of B, correct? Okay. Now at time T, what will be the number of nuclei of A remaining? Okay, the number of nuclei of A remaining would be N0 divided by 2 to the power T upon capital T. Check. N0 divided by 2 to the power time divided by the half-life. The half-life is given to us as capital T. Is that correct? Okay. So at time T, the number of nuclei of A remaining would be N0 divided by 2 to the power T divided by capital T. Correct? Alright. Now it is very clear that the number of nuclei which have been disintegrated, okay, the number of nuclei of A that have disintegrated will be equal to the number of nuclei of B that have been formed. Okay, A is getting disintegrated into B. So A disintegrates, B forms. So the number of nuclei of A which has disintegrated will be equal to the number of nuclei of B which have been formed. Okay, so what is going to be that number? The number is going to be N0 minus N0 divided by 2 to the power T upon T. Do you agree? N0 was the initial number of nuclei. This is remaining. So the difference is the decayed part. So that is also going to be equal to the number of the nuclei formed for B. Correct? And what is the ratio given to us? The ratio of B to A. So this quantity divided by this quantity is given to us as 0.3. So all we need to do is put this into the equation and quickly solve it. Correct? So let's quickly do that. So this is going to become 1 minus 1 upon 2 to the power T upon T divided by 1 upon 2 to the power T upon T. This is going to be equal to 0.3. Now let's quickly solve for this. So if we want to solve for this, what are we going to get? So this is going to become 2 to the power T upon capital T minus 1 is equal to 0.3. Correct? So 2 to the power 2 upon T will be equal to 1.3. Now what we can do is we can take a log on both sides. Okay, so if we take a log, we'll be left with T upon capital T log 2 is equal to log 1.3, and from here we are going to get T is equal to capital T into log 1.3 divided by log 2. Okay, and the question, they don't even expect us to do the calculation, so that's perfect for us. Okay, so we have to leave the answer in these terms. So this is going to be our answer, and what will be the correct option? The correct option is going to be option D. Is that clear? Okay, again emphasizing on the fact that these are all JEE questions, so you can get an idea. They're not going to be difficult at all. if you know the basics, if your fundamentals are clear. Alright, okay, is that giving you some confidence? Right, so confidence is the key here. Be confident, believe in yourself, and focus. That's the keyword here, focus. Don't get distracted by anything at this point. Alright, focus is very important. Alright, so let's talk about the next question. Now the half-life of a radioactive substance is 20 minutes. The approximate time interval T2 minus T1 between the time T2 when 2 by 3 of it has decayed and time T1 when 1 by 3 of it has decayed is. Alright, that's the question. Read the question properly and quickly solve it. Okay, it's a very simple question. You can solve this in no more than 1 minute. Okay, quickly do that. Then we're going to discuss it. Alright, go for it. Alright, let's think about this. So at T is equal to 0, let's say there are N naught nuclei. Okay, at T is equal to 0, there are N naught nuclei. Now at T is equal to T1, 1/3 has decayed. Okay, so that's given in the question, that at time T1, 1/3 has decayed. Now if 1/3 has decayed, how much has remained? 2 by 3 N naught has remained. Do you agree? If 1/3 has decayed, then 2 by 3 N naught has remained. 2/3 will be remaining, correct? Okay. Now at T is equal to T2, 2/3 has decayed. Okay. So if 2/3 has decayed, then 1/3 will be remaining. Is that correct? Is that clear? Alright. So what do we have over here now for for this decay? For this decay, we can write an equation. Okay, so what do we have? We have N is equal to N naught into e to the power minus lambda T. Now what is N over here? The N over here is 2 by 3 N naught, this quantity. 2 by 3 N naught, this is the number of nuclei remaining. This is equal to N naught into e to the power minus lambda into T1. Can you see that? Pretty straightforward. Alright, then for this reaction, okay, or for this integration at time T2, from starting till time T2, what can we write? What is the number of nuclei remaining? The number of nuclei remaining is 1 by 3 N naught. This should be equal to N naught into e to the power minus lambda T2. Is that correct? Okay, now it becomes very straightforward that we have to divide these two equations. Okay, we have to divide these two equations because we do not want N naught in the equation, correct? So we can divide these two equations, or N naught is anyway getting cancelled, but we want T2 minus T1. So for that we'll have to divide the equation. Okay, so if we divide this equation, we are going to get 2 is equal to e to the power minus lambda T1 plus lambda T2. Is that correct? So we are going to get 2 is equal to e to the power minus lambda, and this is going to become, or this is going to become lambda into T2 minus T1. Is that correct? Okay, check the calculation. Check the calculation if the calculation is right. So 2 is equal to e to the power lambda T2 minus T1. Alright, so what we can do now? We can take the log on both sides. Okay, we can take log on both sides. So this is going to become ln2 and this is going to become lambda T2 minus T1. Is that correct? Any problem? Perfect. So we had to calculate what is T2 minus T1. So T2 minus T1 will be equal to ln2 divided by lambda. And what is ln2 divided by lambda? Can you recall? That is the half-life. Okay, that's the relationship between lambda and half-life. So ln2 divided by lambda is going to be half-life, and the half-life is given to us. The half-life is given to us as 20 minutes. So T2 minus T1 is going to be 20 minutes. Is that correct? Right, Alok, yes, you're absolutely right. 20 minutes is going to be the correct answer. So option A is going to be our correct option. Is that clear? Alright, perfect. So we move to the next question. Let's look at this question. Okay. So we have at some instant a radioactive sample S1 having an activity of 5 millicurie or microcurie. Okay, 5 microcurie. Has twice the number of nuclei as another sample S2 which has an activity of 10 microcurie. The half-lives of S1 and S2 are, and that's the question. Okay, the half-lives of S1 and S2. Alright, so go for it, go for this question, quickly solve this question and then we are going to discuss it. Sorry about that. Alright, so let's talk about sample S1 and sample S2. So what is the activity for sample S1? The activity is 5 microcurie and for sample S2 the activity is 10 microcurie, correct? Also the number of S1 is twice the number of S2. So let's say the number is 2n and this is going to be n. Okay, so for the number of nuclei of S2 is n, so number of nuclei of S1 are going to be 2n. Is that correct? Okay. Now what do we need to find out? We need to find out what is their half-lives or the relationship of their half-lives. Okay. Perfect. So let's call this lambda 1 and let's call this lambda 2. Okay. So the decay constant for S1 is lambda 1, the decay constant for S2 is lambda 2. Alright, let's do this. Okay. Now what is law of radioactive decay? What is law of radioactive decay? Law of radioactive decay tells me that the rate of disintegration minus dN by dt is equal to lambda n, correct? The rate of disintegration is proportional to the number of active nuclei. So minus dN by dt is equal to lambda n, okay? Now what is this minus dN by dt? It is the rate of disintegration. Okay. So for S1, can we write it as 5 microcurie? Okay, let me write it over here. There will be much more space over here. Okay, so this is for, I am writing for S1. Okay, I am writing for S1. So the rate of disintegration is 5 microcurie. This should be equal to lambda 1 into 2n. Do you agree? Okay. Now similarly we can write it for S2. For S2 it is going to be 10 microcurie and this is equal to lambda 2 into n. Do you agree? Okay, are you comfortable with these two equations? If you're comfortable with these two equations, then what we can do is we can find the ratio of lambda 1 and lambda 2. Okay. Now if we divide the equations, the ratio of lambda 1 and lambda 2 is going to be 1 upon 4. Correct. So what we get here is lambda 1 upon lambda 2 is equal to 1 by 4. Correct. Okay. Now we don't need this. We need the ratio of half-lives. Okay, we need the ratio of half-lives. So what we can do is we can write lambda 1 as ln2 divided by t1. T1 is the half-life for sample 1, and then we can write this as ln2 divided by t2. This is equal to 1 upon 4. So ln2 and ln2 is gone. So what we do, we get t2 is equal to t1 divided by 4. Okay, that's the relationship of half-lives we have got. Okay, T2 is equal to T1 divided by 4. Now we don't have enough data to find out the half-lives from here, but we are going to take the help of options. Okay, what are the options? T2 is equal to T1 divided by 4. Now we have to check that for which one T2 is going to be 1/4 of T1. Is 10 year and 20 year going to be the answer? No, T2 has to be smaller. T2 has to be 1/4 of T1. 5 years and 2 years, okay, the ratio here is 1 by 4, but T2 is 4 times, okay, T2 is 4 times of T1. Then 20 years and 10 years, the ratio is 2, so certainly not the answer. 20 years and 5 years, okay, so if T2 is 20 years, T1 is 1/4 of 20 years, which is 5 years, so option D is going to be the correct option. Alright, do you follow? Is this clear? Is there any confusion? Is there anything you want to ask me? Please go ahead. I'll be happy to answer that. Alright, now this is the end of this session. Okay, my objective for this session was to make you realize how important this topic is, how important modern physics and all these topics that we are doing is, because it's so simple and we have solved previous JEE year questions. So you understand that this is the level of question that has been asked, and it's very straightforward, that's very simple. So if you do this chapter well, if you get your fundamentals right, then it's not going to be difficult at all. It is going to be very, very scoring. Alright, so that is it for this session. I hope you find this helpful. So very soon I'm going to see you in another session, but till then, keep practicing, keep getting better, and keep your focus on JEE. All the best guys, and thank you very much for watching.